let's go very slow on our chapter 6. And so we're going to cover inner product, length, orthogonality, orthogonal sets, orthogonal projection. The inner product. So let's say we have so you can take a vector in like R4, R3, R2, R5, anywhere you want. In this case, let's go with R4. So just for a quick review. So for us to calculate vectors with a scalar multiplication and addition, so let's say -3 and this much vector 1, 2, 1, 3. Let's go to -2 and like 2, 1, 1, 1. This is where you, so scalar multiply, then you're gonna multiply to each and every component. So 3 times 1 is 3, 3 times 2 is 6, 3 times 1 is 3, and 3 times 3 is 9. -2 times 2 is -4. -2 times 1 is -2, and you get all ones. So multiply, we get -2s. So adding all up, it means that all the components, we do calculations. 3 plus -4 is 3 minus 4 is -1. 6 plus -2 is 6 minus 2 is 4. 3 minus 2, 1. 9 minus 2, 7. It's kind of a very simple calculation. All we want to do here is that we want to do inner product here, and I want to, so in real case, so considering real numbers, so we were very flexible with doing addition, subtraction, division, except for dividing by 0 and multiplication. So those were very flexible. We could almost do like literally everything for real number calculation, which we most of the time call arithmetic. And now we want to extend that to vector. We want to multiply two vectors. But the thing is that instead of real numbers, so for example, like 3 times 2 is 6, for two vectors, it has 4 components. So in order for us to define multiplication is kind of tricky. So what we do is we define inner product and outer product. Well, for linear algebra in this course, we're not going to cover outer product, but we're going to cover inner product. So we put it as like this dot, and what we do is we multiply component-wise and add together. So 1 times 2, 2 times 1, 1 times 1, and 3 times 1. So this becomes 2 plus 2 plus 1 plus 3, so it becomes 8. Okay. So when we multiply So inner product vector. So let's say vector A inner product vector B. So this is length of A times length of B. So by the way, this two line, this notation is a vector notation or bold-face notation that we call. So length of A, length of B times cosine theta, where theta is an angle between A and B. So for example, before we go example, so I'm gonna show you what this length is, and I'm gonna show you how to calculate this angle. Now, let's consider 1, 1, 1 like this. So this is the length of this vector. So it's the square root of 1 square plus 1 square plus 1 square. So it becomes square root of 3. So the reason why it's called length is because it literally is length. So length of 1, 1, 1, and R3. Let's see, here's R3. Let's say this vector is 1, 1, 1. And this length here is square root of 3 much. So applies to R2. We can generalize this to R4, like 4-dimensional, 5-dimensional case, then we can get all these lengths. Likewise, let's go with a length of, let's go with the best possible example that I can think of. So we got a 1, 1, 1. So let's go with square root of 3. Square root of 3. 2. So 1, 1, negative 1. Well, let's go with like 1, 1, 0. Well, just to make it interesting, 2, 1, 0. The norm of this is square root of square of adding all the squares, 2 squared plus 1 squared plus 0 squared. So we got square root of 5. So our inner product 1, 1, 1. Inner product 2, 1, 0. So this is 1 times 2 plus 1 times 1 plus 1 times 0. So it's 2 plus 1 plus 0. So it's 3. Now this is equal to this, which is length of first vector, which is square root of 3. Length of second vector, which is square root of 5. And the angle between it. So that cos theta is 3 over square root of 3 times square root of 5. So square root cancels out, so we get square root of 3 over square root of 5. So let's say we have like a vector loosely, let's put vector 1, 1, 1 here. Let's go with a vector 2, 1, 0 here. I'm just like loosely drawing it without coordinates. And here's our angle here. It has the value square root of 3 over square root of 5. So it basically, so the inner product So the inner product basically tells us the angle between two vectors. That's that's the meaning of it. Yeah, sure. Yeah, you can record it. So we got an inner product here. We can do to this one as well. So we can do to a vector in R4, 4-dimension as well. So length of 1, 2, 1, 3. This is square root of 1 squared plus 2 squared plus 1 squared plus 3 squared. So this is square root of 1 plus 4 plus 1 plus 9. This is square root of 15. So length of 2, 1, 1, 1. This is square root of 2 squared plus 1 squared plus 1 squared plus 1 squared. So this is square root of 4 plus 1 plus 1 plus 1. So this is square root of 7. So that inner product of 1, 2, 1, 3 and 2, 1, 1, 1. So this is, as we calculate, this is 8. There's also a length of this, which is square root of 15. Length of this, square root of 7. And we got this cosine theta. So our cosine theta is 8 over square root of 15 times square root of 7. So of course, this vector, so these two vectors are in R4. There's no way we can draw it like this. But one thing for sure is that we can definitely define length, and we can find angle. This technically it's like the 4-dimensional vectors, and we're finding like angles. It totally makes fine. Totally makes sense, and lots of applications on there. Like so like this vector can be like it can be like in like R100 or 200. It can be like crazy. Happening in a lot of things happening in like engineering, computer science, and economy. Okay, so now we know how to do inner product. Now let's see orthogonality. So orthogonality means that any inner product gives us 0. So let's say 1, 1. Yeah, let's go with 2. 1, 1, 2. Inner product. We want to go 1, 1, -1. Like this. So this inner product thing, we get 1 times 1. 1 times 1. And we got 2 times -1. 2 times -1. So we got 1 plus 1 minus 2, so 0. Hence, two vectors are orthogonal. So why is it called orthogonal? So let's put this here. So 1, 1, 2, inner product, 1, 1, -1. So we already know this is 0. This is also can be written as the length of 1, 1, 2, which we wouldn't care. Length of 1, 1, -1, which we wouldn't care either, and cos theta, and we wouldn't care. because so these are positive lengths. So vectors, it's not a zero vector, so it obviously should have length. We know that this cos theta, this should be zero because the left-hand side is zero. So cos theta equals zero. So by the trigonometry class, I hope you just for a reminder that cos theta equals zero, then theta can be negative pi over 2, pi over 2, 3 pi over 2, and so on. But just taking the angle between 0 and pi, it is pi over 2. In other words, it's 90 degrees. It's a right angle. So let's draw this in the R3. Here's our R3. Here's our X and Y and Z. Let's draw vector 1, 1, 2. So let's put this as 1, this is 1, this is 1, and this is 2. And this vector is going to roughly in like somewhere around here. But this is 1, 1, 2. Let's see this vector. So we got 1, 1, and Z coordinate is -1. Let's pull this to the bottom, and let's put this as -1. And this, it's going to be like somewhere around here. Vector's kind of a bit skewed. Here's our 1, 1, -1. And the angle between them should be right angle, like this. It literally means orthogonal, right? So normal to each other, if I say, or right angle to each other. So we can always think, so we can also think of orthogonal set of vectors. So let's go with 1, 1, 2 and 1, 1, -1. And I'm going to go with 1, -1, 0. So I've already seen that 1, 1, 2 inner product 1, 1, -1 equals 0. So we already checked. So already checked. So let's check the other ones. So we checked these two. So let's check this one and this one, this one and this one. So 1, 1, 2 and third vector 1, -1, 0. So this is 1 times 1 is 1. 1 times -1 is -1. And 2 times 0 is 0. So it's 0. So these two vectors are orthogonal. So checking these two vectors, so 1, 1, -1, inner product 1, -1, 0. So this is 1 times 1 is 1. 1 times -1 is -1. And -1 times 0 is just multiplied by 0, so 0. So 1 minus 1, 0, so it's 0. So you see that all the vectors are orthogonal each other. So from here, we know that the set of vectors is orthogonal. So why is this important? So why should we know it is orthogonal? So orthogonality, you can think of it as strengthening of linear independence. So not only orthogonal set of vectors is linearly independent, it has very nice property that makes all vectors to be represented in a very nice way. Okay. So So theorem is that orthogonal set of vectors is always linearly independent. So these three are linearly independent. So in other words, for these three vectors, we can represent any vector as linear combination of these three. But we're not going to row reduce to get that answer. Well, actually, we can do projection, other method to get this, get the representation of any vector. Let's go to let's go to let's say U is so I'm thinking of like a fancy nice one as possible. Let's go to 2, 1, like 0, for example. I'm making something for fancier. 2, 1, 0. Yeah, let's go with this one. And let's go V1. Excuse me for a moment. So let's go with V1 as a previous three set of vectors. So 1, 1, 2. V2 is sorry, V2. 1, 1, negative 1. And V3 is 1, negative 1, 0. Okay. I already showed that set of vectors V1, V2, V3. This is orthogonal set of vector. So so what we want to do is to calculate. So we call it a projection of U onto V. So in this case, V1. So project sub V1 and we put it U here. So what does this mean? So what we want to do is so here's our U. And here's our, let's say this is a V1 vector. So what we want to do is to put the perpendicular line to V1. We want to make this new vector here. So literally we want to project U to V and make some new vector that's pointing along parallel to V1 in this way. So this vector is our project sub V1 U, like this. So project sub V1 U. So let's think about this one. So let's think about inner product of U and V1. So inner product of U and V1 was multiple of length of UN, length of V1, and angle between them. So it's length of this times length of this times cosine of this angle, which is the same as the length of this times length of this, because this times cosine equals this angle, right? This times cosine equals this. So it literally is this times this. But what we want to do is to make direction into V1 like this. So U times V1 is scalar value. We want to put the, so in order for us to make it as vector value, you want to put in v1. But also, you want to divide v1 inner product v1, which is just the square of length of v1, because cosine 0 is just 1. So so here we're dividing by length of v1 twice, so that the upper one is length of this times length of this, but this cancels out, so we're only left with length of this, but the other v1 length is gonna be divided to this one, so that these two alone represent the unit vector. So the unit vector times the length becomes like this length of vector in this direction. So I'm going to resume. So 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 I have like some of them coming. So I'll resume in 5 minutes. Okay. Okay. So yeah, I'm back. So this is our formula. So projection, if you have one vector and projection to other vector, and this is our formula. So one thing you can remember is that always direction is the one that we're projecting onto. And we want to kind of save the length of u projected to a v1 in this case. Want to kind of divide it, to adjust it. It's kind of a way I remember it. But anyway, so let's calculate this. So this is so u is 210, inner product 112 over, we've got v1 112, inner product 112. We got this vector 112 here. So this is, so 2 times 1 is 2, plus 1 times 1 is 1, and 0 times 2 is just 0. We got 1 times 1 is 1. 1 times 1, 1. 2 times 2 is 4. We got 1, 1. So this is 3 over 5 times 1, 1, 2. So let's look at other projection onto other vectors. So project onto v2 u. So this is u inner product v2 over v2 inner product v2 v2. So this is, so u is our 210 inner product 1 1 negative 1 over 1 1 negative 1 inner product 1 1 negative 1, and we got 1 1 negative 1. Okay. So we got 2 times 1 equals 2, 1 times 1 equals 1, 0. 1 1 negative times negative 1 1, so 1 plus 1 plus 1, and 1 1 negative 1. We got numerator 3, denominator 3 cancels out. So we got 1 1 negative 1. So let's go with a projection v3 u. So u inner product v3 over v3 inner product v3 v3. So this is 2 1 0 inner product, so v3 is 1 negative 1 0. over 1, negative 1, 0. Your product 1, negative 1, 0, and 1, negative 1, 0. So this is 2 times 2 plus 1 times negative 1 is negative 1, so 2 minus 1, and 0 just goes away. We got 1, negative 1 times negative 1 is 1, and 0 goes away, and we got 1, negative 1, 0. So we got 1 over 2, 1, negative 1, 0. So what does this tell us? So why are we doing all these? So as we showed, V1, V2, and V3 are orthogonal. So it forms orthogonal set of vectors. This means that, so loosely speaking, let's try it here. So loosely speaking, all these vectors. So let's say this is V1, this is V2, this is V3. So these vectors are right angle each other, orthogonal each other, like this. So in some sense, they kind of make like new coordinate axes. Instead of X, Y, Z, we can go with like V1, V2, V3. But let's say U is here. So loosely drawing, let's say U is like somewhere around here. Then as we project onto XYZ coordinate, instead we're projecting to V1, V2, V3 is our new coordinate, let's say. Then so let me draw V1, V2, and V3 larger to fit like U nicely with these coefficients. So let's go with let's go with this much as V1, this much as V2, and this much as V3. Okay. So we know that these are all right angles each other. Now let's say loosely drawing, let's say this is V, this is our U. Then let's think about how we get all the XYZ coordinates from any vector in R3. So we pick a vector, and what we do is to project onto XYZ coordinate, which are just obviously it's XYZ coordinate. So for example, let's say here's our X, Y, Z coordinate. Let's say we got this vector ABC. What we did was to project onto x-axis, project onto y-axis, and project onto z-axis, and these are going to be like A, B, and C. So we know that those three has these coordinates. So we can likewise do the same to V1, V2, and V3. Because these three are orthogonal, we can think of this as new coordinate axes. So project onto V1, you know that it's 3 over 5 over, so 1, 1, 2 is our V1, right? So let's like kind of like loosely like chop it up. Here's our I don't know, V1 coordinate, if you want to call V1 coordinate. And this one, so this is just a V2. So it's the whole of V2. This one is the just the half of V3. Let's loosely chop it up. Here's our V3 coordinate of like U1, U. Let's just like put it in that. And let's add these up. So I'm pretty sure it's not going to be like this U. So adding these two vectors, we get like this vector here. Adding this vector to this vector, we get kind of goes like this. So technically so to fancy it up, our u vectors kind of go like this. So let me draw it in like the nicest way as possible. So, straighten this line. Something like this, right? We know that this u is, so likewise, as an xyz coordinate. It's just for a little drawing. So likewise in the xyz coordinate, u can be represented as projection. So sum of all the projection vectors of v1, v2, and v3, which was 3 over 5, 1, 1, 2, plus 1, 1, negative 1, plus half. Or let's represent this v1, v2, v3 just for notational convenience. So this is 3 over 5 v1 plus v2 plus half v3. Okay. This is our linear combination of v1, v2, and v3. So notice that we haven't used any row reduction to represent u as a linear combination of v1, v2, and v3. Right? So orthogonal set, since it's a way stronger form than just being a basis, like for example, like 3 vectors in R3, linearly independent, so basis is way stronger, so that all we have to do is project. And we get the linear combination. This applies to all the dimensions R2, R4, R5, so on and so forth. So let's look at so we're starting to run out of time. So let's look at some example that we project onto plane in R3. So always or in this case, let's go with maybe like 2, 1, 1. So let's go with u equals 2, 1, 1. Let's say v1 equals 1, 1, 0, v2 equals 1, negative 1, 0, and our subspace in R3 should be, so w equals span of v1, v2. So as you can see that v1 inner product v2, so 1, 1, 0, inner product 1, negative 1, 0. So we got 1 plus negative 1 plus 0, so we got 0. So v1, v2 are orthogonal. In particular, set of 2 vectors is, this is orthogonal set of vectors. We see that this w, which is spanned by v1, v2, not only it becomes bases, but it also is orthogonal bases. Right? And so is an orthogonal basis for W. Let's draw this graphically. So here's our x, y, z coordinate, let's draw a v1. So it's 1, 1, 0. So it's gonna be somewhere around here. v2, 1, extend y to the negative side, -1, 0. So here we got v2. And let's draw u, so 1, 1, 2. So it's gonna be somewhere around something like this. Like u. So I'm gonna project into so our w should be space up spanned by v1 and v2. So it practically should be just the xy plane. If you project u onto this xy plane, then it's just going to be v1, right? So graphically speaking, it's just obvious that orthogonal projection of u onto w is just v1. So let's check that. So project v1 u1 v1 u, this is by definition. So 2, 1, 1, our v1 v1 inner product v1 v1. So this is 2 times 1 times 0. So 2 plus 1 plus 0, 3, and 2. 1 plus 1 plus 0 is 2. 1, 1, 0. Projection of v2 u. This is u, and v2 is 1, -1, 0 over 1, -1, 0. Their product 1, -1, 0 and 1, -1, 0. So this is, so we got 2 plus -1 plus 0, so 2 minus 1, and 1 plus -1 times -1 is 1. And we just got 0, and we have 1, -1, 0. So this is 1 over 2, 1, -1, 0. Like this. Oh yeah, so it's 2, 1, 1, right? Yeah, so the picture should be, so x coordinate is here, x coordinate is 2, y coordinate is 1, and z coordinate is 1. And this vector here, so this is our u vector. Projecting it, you're going to have like this vector. Here, so we project it to w, which is just the xy plane in this case. This we call it as a project onto wu. We're projecting onto subspace. We call this as projection of u onto w. So this, of course, is the project v1 u plus project v2 u. In this case, we got these, so we got 3 over 2. So 1, 1, 0 is just v1. And 1, -1, 0 is v2, so half v2. So 3 over 2. 3 over 2 v1 plus half v2. So graphically speaking, so let's go with a 3 over 2. So 1.5 much. And the half of v2, we're going to get like this much, which is this vector. Yeah. Or so we can write in this linear combination, but let's see the actual vector. So this is 3 over 2, 1, 1, 0, plus half, 1, negative 1, 0. So this is 3 over 2, 3 over 2, 0, plus multiplying half, half, negative half, 0. So 3 over 2 plus 1 over 2, 4 over 2 is 2. 3 over 2 plus negative 1 over 2 is 3 minus 1 over 2. 2 over 2 is 1. And 0 just cancels out. So this is our vector when we project u to this subspace. Okay, so we're almost running out of time. So do you have some questions?
Does it have to be related to chapter 6?
Yeah, it is related to chapter 6.
Okay.
So chapter 6 is all about mirror product orthogonal set, how you can use that to represent vectors, how you can project vector onto other vector or other subspace. These are all like kind of process. It can be like a R4, can be an R2, but basic ideas are straightforward, very similar. Project onto it. Get that if it's a formula here, you're good to go. Okay, so maybe I can continue the crash course on crash course tomorrow, on Wednesday, and maybe on Friday. We'll see about that. But, yeah, let's continue this tomorrow, and I'll see you tomorrow.
I have a question real quick
Okay.
about for the midterm tomorrow, or not tomorrow, the midterm on Thursday. What do you think is the thing that we should focus on the most? Because there's a lot of information, especially since it's the Higgian values and vectors. What do you think that we should be focusing on the most? Or what do you consider is the most important?
Um, even though what I say chapter 5 is the most important one among all the linear algebra course,
Mm-hmm.
I definitely you have to know eigenvalue, eigenvector, not to mention definition, but how to so what eigenvalue is. So eigenvalue got to get from a characteristic equation, and you got to solve that, and how you get eigenspace. So eigenspace is null space of A minus lambda I. So row reducing it, you're gonna get set of vectors, and counting all the number of vectors from all the numbers of eigenvalues. If it's less, then it's not diagonalizable. If it's equal, then it's diagonalizable. If it is diagonalizable, then you make it into diagonalizable form. So those are all very mechanical kind of process. Like it kind of goes through R4, R3, R2. Just the matrices have so basically it's just the matter of number. All the processes are very straightforward and the same. For week 7, 4.4 to 4.6, so we covered like a rank theorem. So dimension of rank plus dimension of nullity is dimension of domain, and also for applying that to generalized vector spaces, in particular applying that to polynomial spaces, or in the, let's say, polynomial with degree less than or equal to 3. If you have given 3 vectors Is it linearly independent so that is it basis, or if it is basis, then can you, if you have one polynomial n with degree less than equal to 3, can you represent it in represented by all the elements in basis element? That you do it by putting it into matrix form, row reduce it. You have to be a little bit cautious about putting those in matrix entries. Some people actually like put it in like transposed way. It should be aligned.
Okay.
So definitely chapter 5, those are pretty mechanical and straightforward. Week 7, week 7, yeah, like go through so always a row reduction. Well, most of the time it's all row reduction. Linear algebraic cases are always like if you row reduce, then like 80 to 90%, safe to go. But you need to put like extra bone and muscle, I would say, extra muscle, extra flesh to make it meaningful. It comes with a dimension, and linearly independent or not, or bases, eigenvector, eigenspaces, all that. So yeah, so I would recommend you to stick to a definition and how to apply that. I guess you're good to go.
Okay. Okay. Thank you.
Okay, so if you have any other questions, then thank you for thumbs up. And so any questions?